Use this quiz to assess your understanding of this topic. If you know the answers, you may skip this topic. Otherwise, spend the next 2 minutes exploring the topic and building a deeper understanding of the concept. What's your answer? Let me know in the comment section below. In this short, we will dive deeper into dummy variable trap and explore its nuances. Regression assumes that predictors have a linear relationship with the target and are not perfectly dependent on one another. When predictors are highly correlated, we have multicollinearity. To understand the dummy variable trap, we first need to understand multicollinearity. Multicollinearity occurs when two or more predictor variables in a regression model are highly correlated, making it difficult for the model to distinguish their individual effects. For example, if you have columns for length, breadth, and area, including all three creates perfect multicollinearity because there is an exact relationship among the predictors. That is, length times breadth is equal to area. Regression model works best when predictors provide independent information about the target variable rather than being mathematically dependent on one another. The dummy variable trap is a special case of perfect multicollinearity that occurs when we include a dummy variable for every category, creating an exact linear relationship among the predictors. For example, if we include TL underscore green, TL underscore red, and TL underscore yellow along with an intercept, these variable exhibit perfect multicollinearity because exactly one of the three dummies is always 1. In other words, their sum is always equal to the intercept. By omitting one dummy variable, we break the perfect multicollinearity because the intercept can no longer be perfectly determined from the remaining dummy variables. The dummy variable trap isn't limited to models with just one feature. If a model has multiple categorical features, the same issue can occur for each feature. So, if your dataset has both traffic light and road condition as predictors, we typically omit one category from each and use those omitted categories as the reference categories. Although there is only one intercept, each categorical feature creates its own redundant set of dummy variables. Therefore, we typically omit one category from each categorical feature and use it as the reference category. But what if there is no intercept? Without an intercept, we can generally keep all categories of a single categorical feature. However, when there are multiple categorical features, including all categories can still create a linear dependency. That is why, in practice, we commonly use one fewer dummy variable per categorical feature, with the omitted category serving as the reference category. For models such as decision trees and tree ensembles, this particular issue generally doesn't arise, so all one-hot columns can typically be retained. Thus, there are legitimate reasons why we ever use all categories, mainly when you don't have an intercept or when the modeling framework handles the parameterization differently.